Hi, Poul and Marko.
Hi.
Hi.
Welcome to this recording on MIM technology. We will look deeper into what MIM is and how it's manufactured. What are the possibilities? What are the restrictions of it? I have invited you because, Marko, you are the expert in the injection molding part. Poul, you're the expert on the sintering part. Very often we have seen conflicts between these guys, and I would like to open these conflicts today in our discussion. But first, could you introduce yourself, Marko? Would you start?
Yeah, sure, I can do. Hi, everybody. My name is Marko Maetzig. I'm with ARBURG in Germany, and I work for the company meanwhile in the 25th year. And the whole time I've been working in the R&D area of powder injection molding, which includes metals and ceramics. My background is I'm a materials engineer and did some engineering studies at the University of Technology in Dresden.
Thank you.
Welcome.
And Poul.
Yeah, I'm Poul Søgaard. I'm the, let's say, senior process specialist on metal injection molding, and I'm mostly working with the sintering cycle, debinding. I've been at Sintex for 16 and a half years. And before that, I was a student at the University of ARBURG, where I got a master's in production technology. And also did my master thesis together with Sintex. So it's almost 18 years of experience totally.
Yeah, you were born in MIM.
Yeah, exactly. Yeah.
Yeah.
I've never done anything else in my professional life. No.
Yeah. So first, there are people who don't know the history of MIM. How was it invented? Who did it? Who industrialized it? Can you help me get some insight in that?
Yeah, it goes back. I mean, into the 1930s in the US, they started to do some ceramics work, ceramic injection molding. So it didn't start with MIM, but it did start with ceramics. And there are two major events that are some patents in the 1930s. The one was granted in, or not in the 30s, in the 40s, in 1938 to a US guy working for General Motors on a refractory body and the method of making the same. And the second one is a German patent that was issued in 1940 to a group working for Robert Bosch at that days for a similar process. So that is the how it all started. Then later on, it went into metals as well. And the real push came, let's say, in the 1970s when people like Zuger, Weich, and Malat and Rivers did a lot of work on that and also started to patent that. So from that, it took all off. And the real push happened in the 90s, of course.
Yeah.
When it also got industrialized in Europe with, for instance, BASF stepping into the market as a commercial feedstock supplier.
Yeah. Yeah, that's the one that really make the game changer industrially, at least here in Europe.
In Europe especially, yes.
Yeah. Yeah. So if we look into what MIM is, there are different steps. Feedstock production, injection molding, debinding, sintering, post-processing. If we look into these, what are the different strategies? If we start with the feedstock, maybe Poul, you can give an insight in how you can make your feedstock and what different strategies there are on the market.
Yeah, absolutely. So let's say that the strategy we have at Sintex is that we buy the feedstock as a complete material. So we simply get it delivered where the polymers have been blended with the metal powders, and we work with the BASF system or the catalytic system. But there are other options there. But in general, you can say if you want to be very, very specific on what does a feedstock or the material consist of, you kind of have the main bulk, both in weight and in volume, is the metal powders. And then you need some polymer binders. And in MIM, because you still need a lot of binders. There is a tendency, and most of the system runs like this, that you have two different binder systems. You have let's say a primary binder, and then you have a backbone binder. And this is more important when we're going to discuss about the let's say the debinding, because we kind of need to remove all of these plastics again, because they're not really needed for the final products. So there are different types of systems. Some of them are thermal systems. Then we have the water-soluble system. We have the solvent-based systems where you use something different than water. And then we have the catalytic system, which we are using. And I think also in Europe, Marko, you may have seen more in the European manufacturers than I have, but the catalytic systems are quite popular in Europe, at least.
Absolutely.
But again, also because of the, let's say, the convenience of going into continuous furnaces with the catalytic systems are quite good, because it's a dry process. But we'll get back to that when we're going to discuss a bit more about the debinding. But in general, there's metal powders and there's a binder system, which consists of at least two components in this.
And you said that we buy it from as a pre-blend, but is it normal to make own blends, in-house blends?
Well, maybe not so much in Europe, but let's say where it started and very much in the US, there is a much more commonly used that you do this. And also some of the let's say the big players in the market are also, manufacturing the powders themselves and also do the compounding afterwards. So there, it's different on how you chose your business model. But the European most likely is going to buy a finished feedstock.
Okay. Yeah. And then, Marko, next step is to injection mold it. Is it exactly same machine process as when you make a standard plastic? You can see I have the product behind me, the injection molding made in Lego, the furnace made in Lego. Is it the same process as when you make Lego parts?
Basically, one could say yes, it is basically the same process. Of course, there are some specialties. We have to have some special options on the machine that have to deal with the plasticizing unit. So we have specialized barrels and screws with separate geometries or different geometries than for plastics processing. But the process itself, from how it starts and how it goes on, is almost the same, I would say. So. Of course, every material has got a certain need for a special setup of daters, but that's something that is that holds true for plastics as well.
Yeah, when I have been visiting a plastic injection molding factory and compare that to MIM, the speed is a lot higher in plastic, and I think that is because of the large heat capacity of the metal. So it takes longer time to solidify. How much are we talking here?
That's true. We have, let's say, some really differences in the processing time. With plastics processing, you have very often shorter cycle times as with metals or ceramics. But the reason mainly is, and the main reason, of course, is the physical properties of the feedstock. We have a very high heat capacity, but also due to the heat conductivity, we need to run the materials at higher temperatures. So especially the mold temperatures are much higher than with plastics, and that's why the cooling capacity of the tool is less than with plastics, and that's why it also takes longer to cool it down.
Okay, how much are we talking? Is it 10% or what is a typical elongation time?
I would say it can go up to 30 and to 50%.
Okay, so it's pretty much.
It's pretty much, yes.
Yeah. Then if we go to the debinding and sintering, Poul, there are mainly two strategies. There is a continuous furnace and there is a batch furnace.
Yeah.
Why do some choose one compared to the other?
In general, you say that if you want to go batch furnaces, you get not just a little, but a lot more flexibility. You get in some degrees better control. You can mix and match your parts inside. Where in the continuous furnaces, you kind of have to more or less run the same, not so much because of the debinding, but because of, let's say, the sintering we're going to do afterwards. It's advantage to stay with the same type of parts. So you get a lot more flexibility in the debinding unit. For instance, if you one day run, let's say, smaller parts or larger parts, you can change your process parameters and even do process monitoring in a different way. In the continuous furnaces, because everything is dependent on each other, sometimes you'd spend longer time. That's, let's say, this is the sintering furnace that decides how long it's going to be in the debinding furnace. Sometimes it's enough or way too much, and sometimes you can be on the edge if the part is very thick. So you kind of have to consider the, let's say, debinding is a process that happens from the outside in. So the longer you have to remove the binders, the bigger the part you have, the longer the distance to the center of the part, the longer time it's going to take. So it's really flexible. If you one day run 1 millimeter parts in thickness, the next day 8 millimeters, it's very easy to change your process parameters. In a continuous furnace, you're going to do so every part. You sometimes at least have to do it like you are handling the very thick parts always. So you might do some, let's say, over debinding, because that's the way you build up your process. So that's a general overview of that. But there are things, let's say, so we're discussing this batch versus continuous. The only system that is able to be run continuously, as to my knowledge at least, is the catalytic system. In theory, you could also run the thermal, but that's going to be a lot of gases coming off of this. But the continuous system for the catalytic feedstock is quite efficient. The other solvent and water-based systems are batch systems. So you have to submerge your parts into whatever solvent or water you're going to use. So there, it's more if you decided for the catalytic system, but then you have the option of going continuous. So that's very briefly.
Yeah. Marko, do you have some insight in what are the distributions between continuous and batch? How many companies are going for batch and how many are going for continuous? And is there a difference if we look around the world?
That is not very easy to answer a question, because you will find both technologies all over the world. And especially with the larger players, when you look at them, they more often have continuous lines. But to increase their, as mentioned, flexibility, they also add some batch lines. And also, on the other hand, companies that start with batch, when they grow and have one, let's say, high volume part, they think about adding continuous furnaces. So it's very hard to tell whether there is companies that is only using continuous or only using batches. So it's a very good split, I would say. Of course, finally you will find more batch furnaces than continuous lines, because with all the smaller companies, they have typically batch equipment. But I don't have numbers on that.
No, it's fair. Poul, if we go into the processes, the debinding and the sintering, what is happening with the parts? There's a weight loss in the debinding, but how much is it? Does it change dimension? And then again, during sintering, what happens to the parts?
So if you look into what's happening in the debinding process, it's a matter of losing all the primary binders. And the weight loss depends on which binder system you're using. So if you're talking about the catalytic system, it's typically around 7% of the weight. If you're talking on some of the waters, it's a long time since I've done it last time, but there we're talking between 4 to 5% of the binder you have to lose. And the ratio of how much you need to lose is also how much is the primary binder versus the backbone binders. So for sure, the catalytic system has a very high weight loss because there's only a minimum of, let's say, backbone afterwards. Whereas the water-soluble systems that we've worked with, at least, has a lot of backbone afterwards to keep the component stable and being able to withstand being washed, because you need some movement in the water and so on. So you need some mechanical,
okay.
So it's a bit dependent, but in general, you can say there are also limitations, because the catalytic system is not suitable for copper feedstocks, for instance. The nitric acid, which is used, is simply going to react with the copper, and then you're kind of done. So there are some limitations there. And just going back to, let's say, the batch versus continuous discussion, there are also materials which are better suited for batch furnace. Of course, titanium is much better suited in a vacuum furnace than doing it in a hydrogen furnace. But also, if we had to do, let's say, a copper component, the sintering temperature is so much lower than it is for our, let's say, 316 steels. So the furnaces we have for continuous lines are not really suitable for using for a copper part, for instance. So there are also some technology choices depending on the alloy you need. So just to kind of wrap that up, that there are some limitations in some of these. That's
maybe I can add something. You mentioned that copper is not very good with a catalytic process. On the other hand, I feel that let's say low alloy steels are not working very well with water systems, water debinding systems, because then you need a corrosion inhibitor, and nobody really knows what is left behind. Once you dry the parts. Maybe you get a sinterate, but maybe you don't. So there's pros and cons in all directions.
Yeah,
exactly.
Yeah, fair.
Yeah, and in a second you pour in these corrosion inhibitors into the water system, you also get let's say the residual water from the debinding. You need to take care of this, and that's also something that you logistically have to take care of for the water. Not so much what you put in, but what gets out from the process. You need to clean it, or whatever the local legislation says you have to do. So there are disadvantages in this also.
Yeah. Then, if we look into the sintering furnace, what happens with the parts there?
If I'm going to start, there's like 2 steps, because the first step is we need to remove the residual binders. The last 10% of all the binder system has to be removed very slowly, very carefully, because if it goes too fast, then it's going to turn to gas at once and make cracks in the part. But very slowly, we're going to heat it up. So at the same time, we have evaporation of this binder system. We also get, let's say, a surface bonding of the metal components. And after that happens, we just need to go to the, let's say, the sintering temperature, hold it there for a given amount of time, depending on the system. In most of the cases, it's around 3 hours in a batch furnace. It's a little bit shorter in the continuous furnaces because they work a bit differently. But more or less 3 hours in sintering for 316. And then we go to the cooling stage, and you have a finished component. So it came to seem, it seemed a bit easy, but of course there are a lot of challenges in this process also.
Yeah. And what about atmosphere during the process? Do you have the same atmosphere all over the furnace, or does it vary from the rest debinding to the sintering zone?
In a continuous furnace, it's most likely the same. Maybe some furnaces can add some other gases in let's say the beginning of the zone, but normally if you take a sintering furnace, you put in gas in one end, and then you just kind of pull it through the entire furnace. So we have an entry and an exit. In a batch furnace, you of course have options to choose which gas you want to use along the way. So in theory, you could use a nitrogen atmosphere for removing of the binders, and then switch to hydrogen when you need it. But I would say that that would be very rare that you do this, just in order to avoid any complications. So you'll just do the normal 316 in a hydrogen atmosphere. Sorry. And then of course you have other alloys where you need the nitrogen atmosphere. Then you're going to run nitrogen all the way. So it's easier to just keep it in one atmosphere from experience.
Yeah. Then maybe a stupid question. When the part comes out what kind of post-processing? Do you have to make threads? Do you have to treat the surface? Do you have to remove fins? Do you have to cut off inlets? How much post-processing is really needed in MIM?
Yeah, but that depends on how complex can we make it in the mold. So this comes back to how much are you willing to pay for a mold in the first place. Again,
Absolutely.
how many pieces do you need to manufacture? Are you doing 1 million pieces? Then it might be worthwhile to invest in a more expensive mold where you remove all of the inlets. You don't have any marks or whatever. Sometimes it's more beneficial to run it in a mold where you do manual removal of whatever, either in green state, because you can also machine. The parts can also be machined in just the simple green state, or if you're going to do it in the final state. So that depends. We don't have that much experience with, let's say, post-processing in, let's say, polishing and so on. That's not something that we do regularly, but we have parts where we do microblasting to remove fins or whatever, especially in the green state, not so much in the finished state. Again, depends on, there's a cutoff between pieces, amount of components you need to manufacture, and then the cost of the mold. Kind of have to find a golden spot for a specific customer, a specific part.
Marko, you said when we talked about the invention of MIM, you talked about ceramics, but we also, Poul mentioned titanium, and he has been talking about stainless steel, and you also mentioned low alloy and copper alloys. Is everything possible? Can you make all kind of materials with this material injection molding process?
It's a very good question. The answer is, well, let's say relatively simple. Everything that is available as a fine sinterable powder can be processed. So then you will find some exclusions. For instance, a pure aluminum material will not work because of oxidizing at the surface. So, but of course, aluminum alloys may work because you get a liquid phase sintering and crack all the oxides. So basically, you could say everything that is sinterable and achievable in very fine scale powders can be worked with.
Yeah.
That's a very general answer.
Yeah. So you can make super alloys. You can make
super alloys.
hard metals,
Absolutely,
tool steel.
Yes. So there's a huge variety of materials, especially when you look at the steel materials. You can do, let's say, everything that is available. Yeah. I mean, if you want to have something really specific, then you must be willing to pay for it, because then you get something that is especially atomized only for you, and then of course cost rises. So it's a question of the economics finally, whether it's worth doing that or not.
Yeah, but if I'm on the other side, I don't want anything special. I want the most common alloy on the shelf. What should I go for then?
Well, it's most likely a stainless steel 316 or 17.4 pH. That is the most common material, I would say, that is used in metal injection molding. And then everything behind that will be probably low alloy steels.
So they are the high runners and optimized. Are you in on that, Poul?
Yeah. So let's say from our perspective, we run 80% of all our production is in 316L. And then 15% in 17.4 pH, and then the rest is something else, low alloy, tool steels, whatever there's trials going on for, or like it is. So we also heavily specialized in the stainless steels. Again, comes from the parts we manufacture, made it necessary to do this. So this is the same we see. Of course, there are, I think, especially after the printable, let's say 3D printers are coming with the binder jetting. I at least see a lot more requests from smaller companies saying, we have this alloy, would it be possible to try to sinter this in a continuous furnace? And some of them have some very exotic metals, because now they can really just print what they need. So the amount of powders they need for a trial is also much lower than if we have to do in MIM, because all of a sudden we need 10 kilograms. They can do maybe 1 kilogram instead. So there are some experiments running around.
Yeah.
Yeah.
So now you turn me on. I would like to ask about prototyping. How easy can you make prototypes? And you said 3D printing. That's one way of doing it, or is it something so different that you cannot compare? And Poul, if you take that, and then Marko afterwards, you could go deeper into. Can you make prototype in injection molding easy and fast and cheap? But Poul, if you take the 3D printing prototype, does it match, or are we far away from each other?
So for functional prototyping, it's fine. It has some inherent differences. So there are things that cannot be done in 3D printing. There's also, of course, a lot of things that can be done quite differently compared to the molding. So you can make structures that is not easily made in injection molding. But in general, you have to be aware that when you do the printing and the surface finish of a component that has been printed is not going to be the same as a part that has been molded. So that is the most common thing. So let's say for functional prototyping, if you want to test it how it works, we also see people could we do, let's say, a 3D printing of this and then do a surface treatment. So you get a smoother surface that is closer to what you are going to achieve in injection molding or in MIM afterwards. So especially when you build it in layers, you can see where the layers are. And that is not something that is seen in the injection molded component. But it's a very fast way to go from a very small series production or from an idea to a prototype, maybe do some small series production to see if it works in the market, and then you can escalate it to a mold in the end. So it is a natural progression step to do this. But there are differences. It is not as good as the injection molded parts.
Yeah. So if I want it perfect from prototyping, Marko, can you make prototyping fast and cheap in the injection molding setup?
Well, I would say relatively fast and relatively cheap, because with the injection molding, you always need a tool. You always need a cavity where you put material in to get your final dimensions and final shape. There are different possibilities. You can run, let's say, easy machinable aluminium tools, where you can, let's say, do a couple of dozens shot to 100 or whatever. You could use you could even use printed plastic bodies as a cavity insert inside, let's say, a master mold. That's possible, and then of course you have more flexibility in terms of design. But on the other hand, you have some restrictions because of the physical properties of the plastics as a dual material, so heat conductivity and so on. So cooling is not very easy. And there is a totally other approach that you produce, let's say, some kind of blanks by injection molding and green machine them. But of course, with that, all of that is not as quick as a direct 3D printing process would be.
But when making these prototypes, do you also get the final dimension? Can you make threads? Can you make all these smart things in it?
That again is a question of cost. I mean, if I have to do it, some threads out of a tool that is made from aluminum, then it can become very hard. You can do tools, of course, where you unthread outside of the mold by hand operation, and then is the question whether the quality will be as good as when you do it in the mold. So because then again, cooling plays a role. How long do you wait until you unscrew your part? So you can add some, let's say, problems to the process. Yeah, but of course it is possible. Yeah.
So when we work with MIM, there are so many steps that can influence the final product and the final tolerances. And I have heard often people talk, what are the tolerances? How fine can you go? Because you have this large shrinkage during sintering, but you also have some shrinkage during injection molding. So what is the tolerance chain, and where do these parameters come from?
Well,
I leave that to you.
and that's completely understandable. So we normally say that we need plus minus 0.5% of your nominal measurement for tolerances. That's the rule of thumb. And I'm going to be I would say don't quote me on this, but the injection molding process is much more precise. It's a very precise product, and if you're in doubt, just look at the Lego model behind Peter, and everybody who's played with Lego bricks know they are able to produce components to extremely high accuracy. That is without a doubt. So we have, in comparison to the dimensions, we have a very good point of going into the furnace, because it is very good. So all of what is possible is more, let's say, if you have the mold design and you've run in the mold to a level where you're satisfied, it's more about how is the atmosphere and temperature, and you kind of need to put the parts in, and there's a difference in positioning in a furnace, and also the chemical composition, the amount of binder to metal powder ratio that is being done when they do the blending is influencing how much does it shrink the next time. You try to minimize the effect in the production, but it's always going to be, there's always going to be some variation. But I think injection molding is what gives the least of the variations, as long as you control your process parameters properly in the injection molding.
Yeah. You have the feedstock, the powder itself.
Yeah.
That gives the first step, and then the sintering, the major part of it. Yeah.
That is, and again, and a thing that also happens is just how did you design the component? How is the component going to handle? Where is your center of mass? So if you have a very elongated part and you have a center of mass in one end, then this is not going to move, and this is going to move a lot. So it's going to be much harder with how do you have the shrinkage moving the part around inside the furnace. That's going to give you a lot more variation than what's happening in the mold. As long as you fill the mold to the same level within reason, then I wouldn't give the molding machine for dimensional issues, at least. There it's really a top class process.
Yeah. Now we come to the fun part, because I would like to go into the type of errors that you typically see. Is it the drawing from the customer that are bad because they have sharp edges, or is it something in the injection molding that goes wrong, or where do errors typically appear, and what kind of errors do you typically see in parts? And of course, then how could we avoid this? That's the interesting part.
Basically, you can make mistakes in every step of the process. The design might be not very good from the beginning, so uneven wall thicknesses, sharp edges, all that what you mentioned before. But when we look at things and we see problems with parts, then very often it's related to the design of the tool. Very often. So most of the cases where we have to what we have to deal with is that something in the tool design is not very good chosen. And of course, you can have different problems also in the post-processing steps because of different wall thicknesses and that the debinding is not sufficient, or maybe distortion during sintering because of the mentioned center of mass problems or uneven surfaces of your setters or whatever is possible. So, and in terms of the moldings, in terms of molding, we have all kinds of, let's say, possible failures and mistakes inside the part. That is, let's say, kind of vacuoles inside thick-walled components that are not avoidable because of the physics during cooling down of the materials. When you cannot post-fill in the holding phase, you have very often you struggle with welding line issues because of jetting phenomena from the material during filling of the cavity. And in this case, for instance, has been sometimes proven not to put a core into the mold and to mold the bore that you want to achieve, but to machine it in afterwards, because you cannot then try to avoid that welding line if it comes to a critical point of the component. So post-processing may also help in this direction. You can get blistering of the parts because of different densification in the component. You can have surface finishes because of demixing of powder and binder. That is something that is relatively common with catalytic systems, at the surface at least. And there is a whole bunch of other things that can happen.
Yeah. And Poul, you always said that the errors, they appear after centering, and you are always blamed for it. And now Marko, he took all of them on his shoulder.
You cannot heal them in the process. When once you put an error inside the component at the beginning, you cannot heal it in the process. So that's why very often the problems appear at the end of the process, but they are put into the process at the beginning.
Yeah.
A good rule of thumb when we are saying this is also if the error is random or chaotic, it is most likely the furnace which is doing something, because you can't really find, let's say, cause for it. But if it's very consistent and always the same, it comes from molding, because again, it's a very accurate process. So when it makes an error, if you run it in with an error, it's going to continue making that error. So that is
absolutely.
So that is sometimes quite easy to see, that if you have a small crack from, let's say, ejection marks or whatever, because the ejectors might be pushing too hard, or maybe it's a bit too hot when you try to take it out of the mold. Because if you want to optimize some of your cycle times, all of a sudden people are starting to say, okay, we can, if we can decrease this just a little bit, then you can get more parts out. But all of a sudden you have parts with different wall thicknesses, and some of it is a lot more soft than the other part. And you put some ejection on it, and it's going to leave marks or small micro cracks, which might not even be detectable in the green state. And all of a sudden you have all the parts are coming out with these errors. So for sure that's a thing. So if it's a reproducible error, it's most likely from the molding. Again, part design, how do we design the mold? Which choices did we make? Influences all of this. Dimensions is something else, but these errors that comes, a lot of them are from what we decided to do in the design phase, and how flexible was the customer. That is also sometimes up for discussion, because for us at least, we see most likely the drawing in an almost finished state. So sometimes it's very difficult to go into a discussion with the customer and saying, but these surfaces are not suitable for injection molding. And all of a sudden you have a part which is maybe 80% of the way, but you need to change some radiuses or something in it. And if the design is too fixed, then it's difficult to be a supplier on that at least.
Yeah.
And one of the things we also see is that when the parts gets bigger, or we have these flow seams that needs to go together, we have challenges with the larger parts, that it's more and more difficult. And I don't know, Marko, if you could just tell a little bit about the systems where you change your mold temperature, so you have the same mold temperature as the injection temperature, and then what you do, just to elaborate on this, because this actually removes a lot of these errors at the expense of maybe a little bit longer cycle times, but you get some other interesting options. And this is because we don't have that system,
right?
So it's only something I've seen demonstrated by ARBURG.
Yeah, I guess that you are talking about the dynamic mold heating, or
exactly.
variotherm processing, where we heat up the cavity before injecting the hot material. So we heat up the cavity to a temperature that is close to the, or that is above the melting point of the main binder component, that the material, when it enters the cavity, stays liquid for a longer period of time. And that is very suitable for, let's say, larger thin-walled components, because then they don't cool down so much during the filling, and you have an easier filling. You can distribute the pressure evenly, and you get almost, let's say, equal green density after that. And then when the cavity is full, when the cavity is filled, then we cool down to the ejection temperature, because we need to be under the solidification point of the thermoplastic material. And then we can eject the part. That is very helpful for larger thin-walled components. But of course, there are also some cons, because when you have, let's say, multiple ejectors in it, you will create a lot of flashing, because ejectors normally are not heated up and cooled down. They will stay at the ejection temperature. So you open up the gap because of the thermal expansion of the tool, and then the material flows into that gap. And also, it is not very suitable for thick-walled components, because the physics behind solidification of a MIM part is always being the same. The temperature or the solidification starts from the outside skin, from the skin of the part, and goes to the inside. And when I'm not able to post-fill that, I simply create a void because of the shrinkage of the material. And there's another thing that is very helpful in terms of in terms of the process, that is applying a vacuum into the cavity when you inject the material, because then you can avoid, let's say, issues with weld lines, where you have two streams or more streams of material flowing together. You always push air in front of you, in front of the material, and so the material cannot close completely. With plastics, it's not really a problem, but with metals or also with ceramics, it's a problem, because once you take out the plastics, then you will have a crack at that stage.
So it's not visible in the green state, but after
often you don't see the problem in the green state, and that's why always the sintering guy is guilty.
Yeah. And you would say for some plastic components, let's say having a void inside, again, depending on which level you're supplying it to, but having a void inside might not be, let's say, the worst thing, or doesn't you maybe be able to see it in the surface. If you have a void inside a part that goes into the sintering furnace, this is going to crack the part. It's simply going to swell the part and then make a crack somewhere. So those are completely deadly for a component for MIM. So again, of course, you're not going to supply something for the automotive industry where you have big voids inside, but maybe for some consumer low-grade goods, then it might be possible to even use it as a feature to lose weight. Again, I'm not a plastics guy. But for MIM, they are really difficult to combat.
Then you said something about size when going big in size. What is big for MIM? And when do you say a part is too big to become MIM?
What is big?
Yeah,
I mean, we have seen parts that weigh 1 kilogram of material or more. But typically, what I would say is very typical would be a component around 100 millimeter and below that. And everything that goes above that, I would say, is a big component. We have seen parts that weigh about 300 grams and have dimensions of, let's say, 180 to 190 millimeters in length, 20 by 20 in width and height. But of course, not full material, but the overall dimensions. So that I would call a big component. I have not seen parts much larger than that.
No, and really that, let's say, now we come into some of what is the disadvantage of having a continuous furnace is also that we kind of have a limited surface area also for sintering. So you can't make a continuous furnace where you have complete flexibility. So we are limited in, again, 200 by 200, but we don't produce parts. I have it here. I don't know if it's camera. This is the largest part we make. It's around 120 grams. So this is for us a very large component, but again, we have internal, external threads, and all sorts of details. So it's a complicated part in that manner. So making it larger also would have been really a challenge. So yeah, it's just to say that this is what we normally at, and I think that for a lot of the industry, and if you're looking around for the MIM components, then you are, let's say, an average size of maybe 15, 17 grams or something. So the components are much smaller in general. But there are, of course, applications where these large components can come to life. But then you are also competing with casting and other processes, which might be more economically feasible.
Then if we look into what is really important today in the industry and the society is energy, CO2 reduction. Is this a green process? And comparing to other technologies to produce such complex part, are we saving material and are we saving the planet with MIM?
Well, and that depends on what you're making, of course. So, but if you look into how the general process works, we can say that a lot of the powders we see, or a lot of the material powders you can use, you could actually start by using scrap material as the basis for your material powders. So already there, you don't necessarily have to go out and refine something from the beginning. The second thing is that during the molding, we are able to, as long as we don't put it into the furnace, we are able to reuse the material. We haven't got, let's say, scientific experiments on it, but I don't know, Marko, if you have you ever tried to see how many times can you actually reuse materials until it's completely broken so you can't use it anymore? If anybody has ever experimented, because in an industrial setting, we say, okay, for these 5, 6, 7 times we've tried, and then we didn't see an issue. I don't know where it ends.
Yeah, I mean, I've seen companies reusing the material until it is gone 100%. So that means sometimes a reuse rate of several 100%. But typically, when we talk about systems that you are employing, we have something that goes into 8 to 10 times recycling of the material, and then it's mostly gone, I would say.
And what is the yield factor? I would say the part you showed, Poul, if I should machine that out of a rod, I would guess the yield would be 30% or something like that. Can you beat that?
For this component, I can do this. This is, of course, also this is an extreme component because you have so many fine features on this. It also took some time to get to where it is today, of course. But for this one, I would say good luck machining this one. This is going to be both expensive and time consuming. But of course, there are parts which have less features where you again can compete a bit more with machining. But for a lot of the parts we see, there are quite a lot of machining involved in it in order to. So this one also has let's say another component where it's just a thread and a base plate with some I can't see this. You can't see it, but it has also there's a die being put into it, so it needs these guides and so on. And all of these features are very simple to make in MIM, but in a machining you have to kind of do it. So it has a very good rate of usage, but again, we cannot achieve the tolerances that it can do in machining. So if you have a part you have designed and you've already put the tolerances on the drawing, let's say this is the thing we discuss the most with customers. A lot of people know about machining, not that many about MIM. So when they make a drawing and they put on the tolerances for machining, then we spend days discussing what is actually needed because we cannot achieve what you can do in machining. That's you have to go on a compromise and say you can allow some variations here in order for this process to work. So that's really the downside of the process. So we have a very high utilization rate of the material. We can reuse it, and when we are making the parts normally, we don't have a very high scrap rate either. But you need to be ready to go under compromise if you're used to machining.
Yeah. So the final thing is now, how does the future look for MIM? Are there new solutions in the pipeline? Will MIM take over, or will MIM be taken over by 3D printing, or how do you see the MIM technology in 5 years from now?
That's a difficult question because right now it is really, we have a lot of, or the industry struggles a lot, especially with all the automotive situation and with the change from internal combustion engine to all electric vehicles and so on. So a lot of components disappear or will disappear that is produced in MIM right now for combustion engines, and to replace that with other parts will be hard. And then it will probably require the development of different and new materials. Let's think about magnetic materials, or maybe high entropy alloys or stuff like that. So maybe there is something that can be rising in the future, but at the moment it's really critical, especially with some of the industry that MIM is mainly supplying to.
Yeah, and let's say in the consumer electronics market, the Apple Lightning connector has also been a trademark of MIM, and with all the regulations and going to USB-C, all of a sudden this has also disappeared from the market. So there are some sintering capacity also in that area where they are hopefully using it for another consumer electronics product, and not trying to go into automotive also, because there's, as Marko mentioned, some challenges in automotive right now. One of the interesting things I saw at the EPMA conference was that the amount of defense industries actually using MIM for defense production is rising. So almost a quarter, I think it was, of the European MIM capacity is for defense now, and that has really changed over the years. It has been always automotive, and then industry. But right now we see a change also with the, let's say, the current situation. So it's a very difficult question to see what happens the next 5 years. Yeah, well, that depends on how people act.
But there are some people who say that 3D print will take over. Do you believe that, or will it be a fight, or will there be some settlement, or will 3D print be a way to make MIM easier accessible?
Well, basically, I don't think that there is will be a large fight between the both technologies, because every technology has its pros and its cons. When it comes to really huge amounts of components, then you will not be very successful maybe the next years with doing 3D printed parts. Of course, they also develop in that direction, but on the other hand, it is very attractive for instance, in the prototyping phase, to use 3D printing parts for finding out whether the component will work or not, and then go on to metal injection molding. So I believe on a coexistence of both technologies.
Yeah, and again, there are of course things you can do in printing that is not possible to do in molding. So you can make features.
Absolutely.
That is not possible to do. So you have your own kind of area to work with in that regard. And also, of course, just saying here that you can also mold things that is not possible or very difficult to sinter. So there is always, you can make a very complex part which you can't really support, and then it's going to be difficult. So and in the same way, 3D printing, at least when we talk about the binder jetting. Because that's the fastest one. That's the one who has the most potential to actually make a cheap enough component to be sellable. But you still need to consider gravity. You still need to consider friction. So a lot of the things you can do by completely freedom of design, but you need to confer to the laws of physics within inside a furnace. So you're still restricting complete freedom in that regard.
Yeah. Thank you, gentlemen. We're out of time, but if people now want to learn more about MIM, are they welcome to contact you?
Absolutely.
Yeah, always.
Yeah. So
that's where we're here for.
I'll put your email on the list. So thank you very much. I really enjoyed it. I learned something new today.
That's good.
Great. So did I.
Wonderful. Thank you.
Yeah.
Thank you.
Okay.
Have a good time.
Have a nice weekend.
Yeah.
Bye-bye.
Bye.